Hi, in this video, we're going to take a look at bias-reduced logistic regression. Okay, so specifically, we're going to be focusing on a situation where I have separation or near perfect separation on my data. Now, what is going on here is that with my target variable, I've got two values, zeros or ones, for this one, and it's going to work out that either from one predictor variable or a collection of predictor variables, I can get two perfect subsets where all the ones are in this subset, all the zeros are in this, and I can distinguish these two sets using only the predictor variables. Now, at first, this sounds really, really great that I'll be able to use my predictor variables to perfectly distinguish between things. Not so fast. There's some problems with this. First and foremost, this perfect separation usually is a fluke in the data. It's not an actual feature of the overall population. Also, numerically, from like a computation point of view, this is problematic by how we normally fit logistic regression models, because the system is assuming we're not going to get this good of a response from our data. So now what we're going to do, we're going to deal with this problem by going through and just adding kind of like a penalty term onto it, to what we're doing to our maximum likelihood estimation. Now, what we'll typically see when I have this perfect situation, so pretend that for large X, I have all the ones. For small x, I have all of the zeros, which I'll show in the generate examples in a little bit. Then what's going to end up happening is for the cut point between big and small x is I'm going to get a really large coefficient, a coefficient that just absolutely doesn't make sense for my logistic regression model. And so that means that we can't trust it. Our model is going to tell us things that are more extreme than what will be reliable. And so we'll have biased estimation. Our confidence intervals really won't make sense. Our interpretation will be difficult. So what we're going to do is that we're going to do a bias reduction on this using that penalized maximum likelihood estimation. All right, so my advice overall is, honestly, in general, fit your generalized linear models in the standard way. And if you get any extremely large coefficients, which I have at work several times, positive or negative, refit your model using the techniques I'm going to present below. All right, now here, this is where the original paper is, bias reduction of maximum likelihood estimations. Here is the author. All right, so in standard logistic regression, when the outcome is rare, low prevalence, it can lead to problems with separation or quasi-separation. So for separation, think if I have big X, I get 1 for Y, small x, I get 0 for Y. So I have a perfect cutoff. Now, here I'm articulating just one predictor variable for it, but in reality, we have to consider this for any number of predictor variables, but it's easiest to think in just terms of one. That with my predictor variables, I can partition all the zeros and ones of my target variable apart from each other. That is perfect separation. Quasi complete separation is where we can almost get it, like really, really close. I really don't have like a hard, firm definition for you. As a mathematician, we always want to have like a strict criteria, a strict definition. But we're going to say quasi-separation is where we nearly get a perfect separation, but not quite. Separation occurs when there is a perfect linear relationship between the predictors and the outcome variable, making it impossible to estimate the parameters, honestly, from a numerical point of view. Traditional logistic regression methods may result in infinite or undefined parameter estimates in the presence of separation, or just really, really big values. That's been my experience with R, that you don't get infinite. Like if you were to do pencil and paper mathematics, you would have gotten infinity, but instead you get 10,000, which wouldn't even make sense. Firth's method was developed to combat these problems by penalizing the likelihood function. All right, so some key features of the bias reduction logistic regression. So it penalizes the likelihood. So it introduces a penalty term to the likelihood function to counteract the bias caused by rare events. This penalty discourages the model from extreme parameter estimates and improves parameter stability. So we also get a bias reduction. And so, it's going to be more reliable, especially in situations where we have sparse data or rare outcomes. We'll have improved confidence intervals. Excuse me, I'm getting over a little bit of sickness right now. First method leads to narrower confidence intervals for parameter estimates, which enhances the precision of the model. And so this makes it a lot more applicable to a lot of situations where we want to know about, because frequently our stakeholders want to know about rare events. Those rare events that are really, really big problems are the ones that they're going to want to have us model. And if they're a rare event, it's going to be harder for us to handle with the standard approach. All right, so the bias reduction method modifies the log likelihood function with a penalty term. And all right, so I messed up my latex, but here we're going to have the likelihood minus 1/2 times the penalty term. And down here is the penalty formula that you can see that we're going to take the derivative and square it, then divide by the second derivative, then add that up over all of our observations and divide by 2. And so n is the number of observations, beta is our vector of model coefficients, and here, the log of L is the log likelihood, and where the derivative is a gradient of the log likelihood with respect to the coefficients. And then, of course, this is the second derivative with respect to the coefficients. The optimized process aims to maximize the modified log likelihood, yielding bias-reduced parameter estimates. All right, so the challenge of rare events. In a lot of situations, we encounter problems where the case that we're trying to model is is rare. So, like disease outbreaks, credit card fraud, rare adverse drug events, and equipment failures are all relatively rare, and they're harder to model. So standard logistic regression doesn't tackle these as well. And so this imbalance, can cause serious problems for us as we are modeling. All right, so now let's talk about the types of data that lead to trouble in fitting. All right, so typically when we're doing logistic regression, it's separation and quasi-complete separation that causes problems. So separation occurs when there is a perfect relationship between one or more predictor variables and the outcome variables. In other words, a combination of predictor variables can perfectly predict the outcome. And that sounds great. That sounds like that's what we would want. And really that is, the problem is our model is going to go off the rails because of the numerics of the computations. Now, there's quasi-complete separation. Now, this is a special case of separation where most of the observations fall into one category of the outcome variable for a certain combination. So here it's like almost separation, but not quite. When separation or quasi-separation occur, maximum likelihood estimates for the model parameters become unstable or even infinite. Yeah, I've seen personally it just absolutely explode when I've been trying to model for these situations. Now, the consequences of separation, coefficient estimates can be extremely large, or I say extremely large, it could be positive or negative. We can get what looks like a perfect fit, but it doesn't generalize well. So like we fit our training data and then everything just goes to crud. Everything's perfect on our training data, but goes to crud when we put it on our test set. We get inflated standard errors and wide confidence intervals for the parameter estimates. And so, if I've got 1 million for coefficient estimates, I'm probably going to have a pretty wide standard error on that guy. And so, that's just something that will also come up. And so it'll also be harder to interpret our odds ratio and stuff like that. So when does separation occur? So typically it's going to be when the outcome is rare, and basically just from us not having enough data that the rarer occasions just by fluke correspond perfectly with our predictor variables just because we don't have a lot of observations. Now there's also when there's a strong predictor or a combination of predictors that on the training data perfectly predict the outcome. The sample size is small, making it easier for separation to occur. And also, let's say I've got good predictor variables, but they're actually collinear. So let's say I have 3 collinear predictor variables that individually are really good predictor variables, but as a group, they become collinear. And so then that's going to give me an opportunity for this to happen, that we can have this situation even worse. So how to handle this? So, of course, we're going to want to do our train, validation, test split 100% of the time to make sure that we're checking these aspects, protecting ourselves from, checking to see that our data, our model will generalize to unseen data. And using a bias reduction method will greatly improve what's going to happen for us. All right, so let's go ahead and create a data set and build some models on this. And I'm going to go ahead and just build a baseline model to compare. Now I'm going to create I'm going to create a data set here. I'm going to have 10,000 observations in the full one. The small data set will only have 10. So 10 is a very small data set to work with, but there are cases as a data scientist, I find myself in that position. And what we're going to do is I'm going to generate perfect separation. So if the predictor variable is negative, it's 0. If the predictor variable is positive, it's 1. So this is big data. I'm generating this to create examples to show you. Now for quasi separation, what we're going to do is I take the 2 closest to 0 and switch it so that it's close to separation, but not quite. So this way, it'll be 1 point away from perfect separation. And for the non-separated data, what I'm going to do is I'm going to let things be 0 if it's less than negative 3.3, 1 if it's greater than 3.3, and everything in the middle is going to alternate back and forth. And I'll show a picture of it. All right, so for separation, this is with my larger data set. You can see I've got up here, it's always 1 whenever X is positive, and it's always 0 whenever X is negative. Now for quasi-separation, there's 1 point here that's with a negative, but it's covered up. So there's a negative X that has a dark point here, and then except for that 1 point, the rest are perfectly ones. Here, down here are all negative X except for 1 positive in here. So the 0 for the target variable has all negative X except for the endpoint, and the ones for the Y have positive X except for the one endpoint that we can't see. And then non-separation, you can't really see it as well here, but you can see that there's overlap between these very well. And it was actually done with an alternating approach to get this the way we want it. You can see that it goes up and down here. If I go do like that, that's how I generated it. All right, so I'm going to go through, train a bunch of models, and we're going to use the bias reduction generalized linear model package, so BRGLM. And so this is going to fit binomial response, generalized linear models, and by removing the leading term from the asymptotic expansion of the bias of the maximum likelihood estimation. So fitting is performed using a pseudo data representation for estimation in binomial response generalized linear models. The bias reduction method is an improvement over traditional maximum likelihood estimates because of the bias reduced estimator is a second order unbiased and has smaller variance than the maximum likelihood estimator. And the resulting estimates and their corresponding standard errors are always finite, with the maximum likelihood estimates can be infinite. The models can be fitted using one of two methods. So we have penalized likelihood, which uses Jeffrey's prior, or we could use the bias reducing modified score. All right, so let's go ahead and fit some models. I'm going to go through and to show you the output. So here I went through, I put all of the models in the, so I fit a whole bunch of models. They're just kind of floating in my workspace. After I did that, I realized, man, I really should put this all into one list. So I'm going to use some code to grab everything that's in there and use a get function to put them all into a list. And then put them into one nice clean list together. And so that way I can extract things in one clean shot. All right, and here I'm just setting up the plot. All right, so now, see if I can fit everything. Yep. Okay, so remember I've got small data set, big data set. And I have separation, quasi-separation, and non-separation. Okay, so separation is the extreme situation where perfect, if I know the X, I exactly know the Y value. And you can see that much bigger than the rest, absolutely huge. Here's 20. So when I have the smaller data set, the maximum likelihood estimate isn't as extreme because it doesn't have enough of a signal from the data to go off the rails. But if I look at the regular data set, 7,000 for a coefficient? No way. There's no way that's right. That is incorrect. That doesn't make sense. And so with the small data set, we can see that the generalized linear model definitely, or with separation, I should say, with separation, the generalized linear model just doesn't work out. Now, when we look at the regular data set, the larger data set with perfect separation, we're still not really that great with the two ways that we fit the model. We both have over 1900. Still pretty big. If I saw that, I would be suspicious of it. These algorithms did much better with the separation of the small data. Here I definitely consider that's trustworthy. This is too big. Even though I would, this would lead me to think that it's statistically significant, I wouldn't trust these numbers. I wouldn't, but now if we go on, when we have quasi-separation, you can see that with a large data set, quasi-separated, it still gave me some extreme values. And so it's not as bad as it was for regular separation. But remember, I only took 2 points and moved them. That's the entire difference. Now, when I have small data sets, now everything worked out about how it should with quasi-separation. I was really impressed by this. I was expecting something worse. And then with non-separation, everything looks pretty clean on the small data set, but the BRGLM algorithm actually didn't do so well. And so we can see in this particular case, BRGLM didn't do as well as GLM did. But over here, these three GLM did worse. So, this is just giving us tools. If I go out, I fit a model, I see an extreme coefficient, I know there's probably something wrong, there's probably separation. What I should do is I should go and try a different fitting algorithm, a different fitting function in R. And so I could jump to BRGLM, I could jump to PL, do whatever works for you, what works for your stakeholders. Now, here are some other packages that we can use for this purpose. I've used VGAM quite a bit personally, and it does offer some bias reduction options. It's one that it is always delivered for me every time I've tried to use it. All right, so for homework, take your data, fit a model, fit the same model using a bias reduction method, compare your models, and post it onto Canvas. All right, well, that's all I've got for you. Life is short. Do math.